sky, we're no longer content with simply observing the distant stars and planets. Our curiosity and ambition have driven us to explore beyond the boundaries of Earth, venturing into the vast expanse of space. But as we contemplate long-distance space travel, the kind that will take us beyond the moon to Mars and beyond that, it's important to understand both the incredible challenges and the scientific advancements that are shaping our journey into the cosmos. The history of space travel is relatively young, yet it's been one of the most extraordinary achievements of the 20th and 21st centuries. The story begins during the Cold War, when the United States and the Soviet Union competed for supremacy in space exploration. In 1957, the Soviet Union launched Sputnik 1, the world's first artificial satellite, into orbit. This event marked the beginning of the space age and ignited the so-called space race. The United States responded with its own space program, and just over a decade later, in 1969, American astronaut Neil Armstrong became the first human to set foot on the moon, a defining moment in human history. Since then, space travel has progressed steadily, with missions to explore the planets and probes to the outer reaches of the solar system, and maintain a continuous human presence in space aboard the International Space Station. However, despite these accomplishments, the dream of long-distance manned space travel, sending humans to Mars, establishing bases on distant moons, or exploring asteroids, remains elusive. The challenges are immense, but the possibilities are equally awe-inspiring. To understand why long-distance space travel is so difficult, we first need to consider the fundamental problem of distance. Space is vast, far beyond anything we experience in our daily lives. For example, the distance from the Earth to the Moon is roughly 238,855 miles. A satellites, but they're not practical for interplanetary journeys on the scale of Mars or beyond that. Researchers are exploring alternative propulsion methods that could make long-distance space travel more feasible. One of the most promising technologies is nuclear propulsion. Unlike chemical rockets, which rely on burning fuel, nuclear rockets use the heat generated by nuclear reactions to expel propellant at much higher speeds. This allows for greater efficiency and faster travel times. NASA and private companies have been investigating nuclear thermal propulsion, which could cut the travel time to Mars in half, making the journey more manageable for astronauts. Another concept is ion propulsion, where charged particles are expelled at high speeds to produce thrust. Ion engines are extremely fuel efficient, but they provide much lower thrust than chemical rockets, so they're more suited for deep space missions where gradual acceleration can build over time. The second major challenge is life support. On Earth, we are surrounded by the necessities of life: air, water, food, and a stable environment. In space, all of these things must be artificially provided and maintained. A spacecraft traveling to Mars or beyond would need to carry enough oxygen, water, and food to support its crew for months, if not years. Recycling systems would be essential to minimize the amount of consumables that need to be carried. The International Space Station has provided valuable experience in this area, with systems that recycle water from urine and sweat and scrub carbon dioxide from the air. But scaling these systems up for a Mars mission presents additional challenges. Moreover, a spacecraft traveling to Mars would not have the luxury of regular resupply missions from Earth, so all of the resources would need to be carefully managed from the outset. Radiation is another significant concern. Earth's atmosphere and magnetic field protect us from harmful cosmic rays and solar radiation. In space, however, astronauts are exposed to much higher levels of radiation, which can damage cells and increase the risk of cancer. A journey to Mars would expose astronauts to radiation for an extended period, especially during periods of heightened solar activity. Developing effective shielding to protect astronauts from this radiation is an ongoing area of research. Some concepts include using water or other materials as a protective barrier, or even using the spacecraft's fuel as radiation shielding. The psychological effects of long-distance space travel can't be overlooked either. Astronauts on a Mars mission would be isolated from Earth for years, with only limited communication with mission control due to the time delay. Signals between Earth and Mars can take anywhere from 4 to 24 minutes to travel one way, depending on the planet's relative positions. The crew would need to be highly autonomous, capable of making critical decisions without stresses of such a mission. Let's talk about Mars, as it's the most realistic candidate for long-distance manned space travel. Given the distances involved and the challenges I've mentioned, a manned mission to Mars with current technology would likely be a one-way trip, or at least a long-term stay. The surface of Mars is cold, with average temperatures of around negative 80 degrees Fahrenheit, and its thin atmosphere is mostly carbon dioxide, making it impossible to breathe without a spacesuit or habitat. The lack of a global magnetic field means Mars is also exposed to high levels of radiation, much like space itself. One of the biggest challenges for a Mars mission is the need for self-sufficiency. Even if we could send enough supplies to Mars to sustain a crew for a few years, a long-term presence would require us to live off the land, so to speak. The scientists are exploring ways to extract water from the Martian soil, which contains traces of water ice, and to produce oxygen from the carbon dioxide in the atmosphere using processes like electrolysis. Food production would also be a challenge. While plants can be grown in greenhouses, they would need protection from radiation and careful management of light, temperature, and nutrients. The resources needed for long-distance manned missions to other parts of the solar system would be even greater. Take a mission to Jupiter's moon Europa, for example. Europa is one of the most intriguing targets for exploration because it's believed to have a subsurface ocean just beneath its icy crust, which could potentially harbor life. However, Jupiter is over 365 million miles from Earth, and the radiation environment around the planet is extremely intense due to its powerful magnetic field. Any mission to Europa would need to carry significant shielding to protect the crew from radiation, and the long travel time, several years, would require a spacecraft that is almost entirely self-sufficient in terms of life support. As we look to the future of long-distance space travel, the prospect of establishing a permanent human presence beyond Earth raises profound questions. For example, if we are to build colonies on the Moon, Mars, or other celestial bodies, how will we ensure the safety and well-being of those who choose to live there? How will we govern these colonies? Will they be extensions of Earth's nations, or will they form their own political systems? The answers to these questions aren't clear, but they're questions that we need to consider as the reality of space colonization comes closer. In the more distant future, the concept of interstellar travel, traveling to other star systems, space